Yeah, today I will be sharing in the next 12 to 13 minutes. I will share some results from the diagnostics of 2-meter temperature assimilation in the operational Kenda CH1 system at MeteoSwiss. So in the operational Kenda CH1 system, we have a variety of observations being assimilated operationally, which includes near surface variables like 2-meter temperature, 2-meter humidity, and surface pressure. The computational, the NWP domain is shown in the right side. The driving model is Icon with lateral boundary conditions coming from IFS. And the second picture, the right side picture, which shows that the typical spatial distribution of different observations which are assimilated within the Kenda CH1 system. We have 40 ensemble members plus one deterministic member, all at 1.1 kilometer resolution. And we have a hourly cycling DA system, which uses LETKF approach. And with respect to the near surface assimilation, surface variable assimilation, we have seen a very good positive impact on the forecast of fog and low stratus with the with the assimilation of near surface variables. But still, we have seen visible degradation of the analysis with in some cases, which basically resulted in a very poor fit to which resulted in a very poor fit to the radio source. And the questions which we want to address, two questions which we want to address is given the known model biases or deficiencies and the very dense surface observation network and the complex topography which is encountered within the Icon model domain, we want to answer whether we can optimize the Kenda system, that is tuning the localization, radius, observation error, inflation, etc., to reduce the impact or negative impact of this 2-meter temperature assimilation. And second question is, can we employ some kind of station selection strategy to flag stations which could not be optimally assimilated because of presence of a model bias or representativity issue? So these are the two questions which we want to answer. And in order to do this, we have been using several diagnostics like model and observation space diagnostics. On top of that, we have been using the cross-validation diagnostic. Cross-validation diagnostics was developed at DWD by Olaf Stiller, who is having a talk at in today's session. So I'm not going much deeper into the details of this method, which I believe Olaf will present again. So basically, it's an observation space diagnostics to assess the impact of a given set of observation against a verifying truth, which is again verifying observations like radio sound. For on the right side, you can see a very, very simple illustration of this approach. So at T0, we assimilate a given type of observation YA, and then we look at the forecast after assimilating this particular observation at T0 plus T, and we have a verifying truth like YV, which is a radio sound for instance, and we see whether the assimilation is pulling the forecast towards the verifying truth or away from it. So that's what we are basically looking at. And the formulation allows such that we have it results in two different terms, sum of two terms, JB A and JAB A subscript A. So we are more interested in this JB term because the JB term basically signifies how we expect this we want this JB term to be positive, which means that the assimilation of a given set of observation actually pulls the forecast towards the verifying truth. And the name suggests the cross-validation is basically refers to comparing the values of JB against its reference values, which is given by the last formula. And comparing these two terms basically amounts to comparing the error covariance estimated between the verifying observation and the assimilated observation from the observations versus the background ensemble estimated variance. And this is what is shown here is the very general formulation, but in the actual implementation in the cross-validation tool, we use the single observation equivalent where we assume that we are using only a single, we are assimilating only one type of observation, not with all the other operationally assimilated observations. And we focus on, instead of focusing on the impact on the forecast, we focus on the impact on the analysis. So the well-known problem with the T2-meter assimilation is revisited with the help of this cross-validation diagnostics. And we choose a period of 3 months period, like October, November, December 2023, to use this cross-validation tool. And what is shown below here is the JB term, which is basically binned in latitude and longitude bins. In each bins, we have so many different surface stations, and when we have positive values, that means those observations are pulling the analysis in the direction of radiosonde. When we have negative values, like in the dark brown colors, we are pulling it away from the radiosonde. The analysis being pulled away from the radiosonde. So we can see over the 3 months period, what we can see is we can see a very visible degradation in the analysis. We can see a lot of brown colors here. And this again confirms what we have already seen in terms of the radiosonde verifications. And on the right side, what you see is, because this is a statistical technique, we can use the cross validation to do different types of binning, which would allow us to interpret different kinds of interpretation. And what is shown here is one interesting binning, where we bin the JB, and the other is the reference term in terms of the horizontal distance from the radiosonde. So what we see here is the blue color is basically the JB term, which is a proxy for the observation estimated covariance, and the green color is basically a proxy for the ensemble estimated covariance. What we see is after 25 kilometers of distance from the radiosource, we see that horizontally, we see that the ensemble covariance starts to have a large mismatch. So it should be noted that in our operational system for the surface observations, we are using a horizontal localization scale of 50 kilometers. So this again points to a possibility that we may have to reduce, at least for the surface observations, surface 2-meter temperature observations, that we may be using a very large localization scale. So we may have to reduce the horizontal localization. And on top of this binned statistics, we have also recently implemented the station-wise diagnostics in the same cross-validation tool, which allows us to look at each station separately. So for example, as I showed earlier, we are now, in the rest of the presentation, I will concentrate mostly on the Po Valley, results from the Po Valley. So here what we are seeing is the verification of stations within some 50-kilometer radius from the Milan radiosonde, which is marked by X. And the color basically represents the JB term. When we have red, which means we are degrading the analysis, and when we have blue, it's better. And the size of the each field markers is basically represents the error. We have a smaller size, that means we have a very large estimated error, and we have a larger size, that means they are statistically significant. What you can see immediately is that most of the stations here, even though all these stations are lying in the very flat terrain, like below 950 hectopascal height, we see a large degradation from most of the stations. And we should also note that some of these stations, even though they are in a very lower levels, but they are present between two orography, like in a valley or somewhere close to the orography, like here. And then we looked at further to understand is there any diurnal variability of this impact. So we did this station-wise diagnostic, repeated this for 0 and 12 UTC, because we have the radio sounding at these 2 times again. And then for the same 3-month period, we did this diagnostic. What you can see interestingly is that we have a very strong degradation during the night time compared to the daytime. And because in the nighttime, we expect temperatures to be much colder than the daytime, we further looked at diagnostics, which would allow us to see if there is any systematic dependence of this impact with respect to the observed surface temperature. So then we went on to do the diagnostics in the observation space, where we collected all the O-B over the 3-month period from the actively assimilated surface stations, basically these stations are basically some 38 odd stations around the Milan radius sound. And then what we see is that what is plotted in the left side first plot is the binned values of O-B with the binned T2 meter values. The colors basically represents the number of data points at each bin. And what you see here is the red line here, which is basically the systematic or conditional bias at each observed 2-meter temperature bins. What you see is that when we go to colder surfaces, we see a large negative bias in the O minus B. And then to put some physical, first we wanted to see if this is coming because of some kind of saturated conditions like fog or anything. But here what you see in the bottom for the same data points, we have the observed relative humidity also from the station. When we bin the relative humidity with respect to temperature and the color, so basically the O minus B in temperature, we see that it's not necessarily correspond to any kind of saturated condition. So we see some systematic biases at the colder near surface temperatures. Then we also wanted to confirm this in terms of the cross-validation tool because it allows us to use different binning. So we wanted to see the same result. What we see from the cross-validation is the JB term is becoming more and more negative. So that means there is a more stronger degradation when we assimilate observations which are over colder temperature, when we assimilate very cold surface temperature observations. So and then then we move to the spread, the analysis of the spread, because spread is an important parameter in the ensemble data assimilation, the data assimilation context of data assimilation. So here again, what is shown here is the binned values of spread with respect to binned observed 2 meter temperature, with colors, darker colors representing the density of data points. And the red line here shows the average spread at each observed T2 meter bins. What we see is that we have a larger ensemble spread when we go to a colder surfaces. So which would eventually allow the model, which will eventually allow the Kenda system to add more increment. And what we are trying to understand now is that how this larger spread again interacts with the other observations, increments of the other observations, and how this is basically resulting in a degradation. That is something which we are still looking at. Since so much has been done about the observations, and we are looking at a very 50-kilometer radius where we have 38 stations. So we wanted to see how the observed temperature from each of these stations look like. So first we tried to bring the observed value itself over a period of 1 month. What is shown here is just for December 2023, where we bring this with us at each analysis time with respect to analysis time. What we see is 2 different clusters. So then when we look at the station wise, that is for each station, when we look at the monthly average diurnal cycle kind of temperature, what you see is that there are certain stations which tend to cluster, which tends to have very, very cold observations compared to others. So this possibly shows that some of these stations which are locally located in valleys or somewhere close to orography are more dominated by local meteorological phenomena, which would point to a possible issue with the representativity. Then to summarize, so we looked at the diagnostics of the operational Kenda CH1 system, and we revisited the 2 meter temperature assimilation problem using the cross-validation tool, which acted as a guidance to locate at which geographical areas we have to constellate. Then we used further diagnostics on the Po Valley to see this negative systematic bias with respect to O minus B, where the bias tend to be more negative when we have more colder surfaces. Further, we could see we also see the issue of the representativity when we have stations in the valley or some closer to the orography. And we also did diagnostics over the Payan region, which is much more dominated by orography, which is not shown in this presentation in the context of time. But all these things put together points to a possibility that we need to reduce the localization at least and we need to have a better station selection strategy to optimally use the surface stations. Some of these tests are still underway, and we look forward to present some of the interesting research in the ISDA conference. And thank you for your time and attention. I will take some questions now.
Yeah, thank you very much, Krishna. For this, I'm really impressed by how carefully you look at individual radioforms, how you scrutinize your observing system. But I guess you, with the orography in your Swiss domain, you have a much more difficult situation than we have. We have on average in Germany, for example. There is, I think, Bruce Ignaty is asking a question in the chat. He wants to know, he's wondering the larger spread problems at low temperature are probably linked to inversions, but at ESMWF we also see more benefit from on 2-hour, 12-hour 2-meter temperature forecasts from such difficult cases. So that seems to be more common from Bruce.
Okay. Yeah, we also have this same inversion things linked to it, especially over the Payan region, which I did not present today. That's a very clear case of inversion during the June, July, August period. We have this inversion thing, and yes. So what we possibly look at in the ensemble itself has a different correlation structure, especially the vertical. So that's why I mentioned that we wanted to see how the localization, especially the spreading the information to a very smaller radius and testing it with a different configuration. That's what we are looking at. Yes.
Yeah, thank you very much, Krishna. I think we better move on in the interest of time. I was not